Okay, one more time. Catalan, numbers. I've kept you in suspense long enough about what in the world this formula is going to end up being, but I promise it will be worth the wait. Okay, so let's get to it here. And I will screen mirror this thing and we will be off and running. So again, we started and we had the Catalan recurrence, you know, that thing, remember, once again, that was just the number of ways to count it was the number of ways to multiply in numbers together. So basically the number of ways to parenthesize those numbers without moving them around. Okay, there was one way to do one number, one way to do two numbers. We wrote down a generating function for that. We found an identity for it, and we used that algebraic identity, namely that the square of the generating function is equal to itself minus x. We used an algebraic derivation on that identity to come up with the generating function, namely that it's 1/2 minus 1/2 times the square root of 1 minus 4x. And then we said, well, how do we deal with it? And we said, well, 1/2 minus 1/2 times, that's basically 1 plus the quantity negative 4x, all raised to the 1/2 power. Well, it turns out that that led us to explore the general binomial theorem, where I have a power on a binomial that isn't necessarily an integer. And we came up with this. And the Pochhammer symbol is what we were led to, sometimes called the falling factorial. It could be any number at all. It's basically like a put. It's like alpha put in, but alpha doesn't have to be an integer, okay? And that was the formula we came up with. But that wasn't all. We knew that we needed specifically to know what was going on with alpha put in, or alpha Pochhammer symbol in, or alpha falling factorial in, over in factorial, really, because that's what appears in the general binomial theorem back there. And we came up with this formula after a little bit of manipulation. Okay, so let's use all these facts to come up with our ultimate conclusion here. So let's start a new page. Okay, so we know that c of x is equal to 1/2 minus 1/2 times the square root of 1 minus 4x, but I'm going to write that as 1 plus the quantity negative 4x, all raised to the 1/2 power. And then we use the general binomial theorem, okay, to write this as 1/2 minus 1/2, okay, open parentheses. I'm going to use the general binomial theorem here. Well, this is going to be, a 1 plus thing raised to the 1/2. I used the general binomial theorem. It's going to be 1 plus, okay, and it's going to be alpha falling 1, our alpha is 1/2 here, over 1 factorial, x to the 1, but x here is like negative 4x. Okay, so it's negative 4x. Okay, plus 1/2 falling 2 over 2 factorial, negative 4x to the 2, plus dot, 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 okay? Plus, etc. We see the pattern. And one thing that we immediately notice is that this 1/2 right here, the first 1/2 in the equation, cancels with the negative 1/2 distributed to the 1. Okay, so like this 1/2 and this 1 end up canceling each other. Okay, so what we end up with here is basically negative 1/2 times, okay, I'm just going to write the generic term here. It's the 1 is gone, and then we're off to the races with the pattern that we see here. So it's going to be dot, 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 plus, okay, and let's invoke the formula from the last page for 1/2 falling in, for 1/2, well, actually, no, I'll just write it down. So this is 1/2 Pochhammer symbol n over n factorial, and then it's negative 4x to the n. I'll write that as negative 4 to the n, x to the n. That is what the generic term is here, okay? Okay, that's what the generic term is. And now we could go back to the previous page where we had our formula for 1/2 falling in over n factorial. Okay, I promise I have that committed to memory here, so we'll easily be able to transfer that over, okay? And actually, we'll go to another page here. So let me go to the next one. So what we discovered is that Cx is equal to negative 1/2, okay? Okay, and what is it? It's 1/2. Let me just write it down. 1/2 falling in over n factorial, negative 4 to the n, x to the n, plus, etc. Okay, I'm going to go ahead and plug in what 1/2 to the n is. Okay, so this is negative 1/2, blah, blah, blah. Here's the generic term. It's going to be negative 2, okay? And then negative 1/4 to the n, okay? Negative 1/4 to the n, which is very convenient because I have a negative 4 to the n sitting right there to cancel some stuff. And what else did we have? So okay, so negative 2, negative 1/4 to the n, and then it was like 1 over n times 2 quantity n minus 1, choose n minus 1, okay? And then this thing is also multiplied. I'm running out of room here. This is negative 4 to the n. But it's okay, some stuff is going to cancel here for us in just a sec. So here we go. Now, look at this. If I distribute the negative 1/2 into here, guess what? This and this cancel. And also, this and this cancel. Okay? So in the end, what we end up with is the generic term is, all this junk cancels and you end up with 1 over n, 2 times the quantity n minus 1, choose n minus 1. How simple that is. X to the n plus dot, 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 dot. Okay, and you might say, okay, wow, big deal. We have a simple thing, but what in the world were we even trying to do? Well, remember, we wanted a formula for C sub n, and we just came up with a formula for C at x, right? That where we have a formula sitting next to x to the n. Okay, so let's bring this home here. So remember that C of x was equal to C1x plus C2x squared. Okay, C2x x squared. Oh man, that's horrible. Let me erase that. Okay, C2x squared plus C3x cubed plus etc. But we just also discovered that the generic, right? So in other words, the generic term here is Cn x to the n. But we also just discovered that the generic term is just 1 over n times 2 quantity n minus 1, choose n minus 1, x to the n, plus etc. So what does that tell you about this? And what is that? Okay, these terms are the same, and therefore the coefficients have to be the same. So the conclusion is that Cn has to be equal to 1 over n times 2 quantity n minus 1, choose n minus 1 for n equal to or greater than 1. N equal to or greater than 1. There it is, right there. There it is, right there in all of its glory. Okay, that is an amazing formula, an amazing formula. All of it gotten at through some generating function manipulation. Let's test it out here. That's always a good thing to do. Okay, so let me just write it down just for good measure. Cn is equal to 1 over n, 2 times the quantity n minus 1, choose n minus 1. And this was good for n equal to or greater than 1. What should C1 be according to this formula? We'll check it out. 1 over 1, 2 times 0, choose, right? So this is like 0, choose 0. Okay, how many ways are there to choose 0 objects from 0? Well, 1, you just don't do anything. So it gives the right answer even in the case of 1. What about 2? Well, for 2, it's going to be 1 over 2. If you plug in n equal to 2, that's 2 minus 1, which is 1. 2 times 1 is 2. So this is 2, choose 1. That's 1/2 times 2, which is 1. What about C3? Okay, before we get ahead of ourselves here, let's think about what C3 should be. Okay, that's the number of ways if I had three numbers multiplied together, A, B, C, okay, the number of ways to multiply this out. Well, I either am going to parenthesize the first two and then take the result and multiply by the third number, or I'm going to parenthesize the last two and multiply that and then multiply that by A. So C3 should be 2. C3 should be 2 if all is right with the world. Okay, and let's see if this formula gives us that. It's 1/3, okay, 1 over 3 times 2 times 3 minus 1, 2 times 2, so that's 4, choose 2. 4, choose 2 is 6. 1/3 times 6 is 2. And that is good news. That is good news for us. Okay, I'll let you kind of play around with this formula a little bit, but that is a remarkable thing to behold, right? So that is, eye-popping. Okay, so there's some eyes, popping out, right? Look at that. Look at that thing right there. Wow. Okay. That is amazing to think about that. Okay, mind blown, right? Hopefully that's a satisfying conclusion to, I guess a sort of a lengthy discussion, but I think that this is a fun little application of the sorts of things that we've been talking about in class, but it's a little bit, outside of, what I would consider to be standard material in a beginning combinatorics course, just because it's pretty specialized, but it allows us to stretch our legs a little bit, use what we know, and see some interesting stuff. Okay, so hope you enjoyed it.